calculate a piece of gallium arsenide under very strong excitation and evaluate its scale at 1.5 eV. Since we are pumping a bulk of gallium nitride, it's a bulk, so it's heavy hole and the light hole is in touch. So we cannot really neglect the heavy hole and the light hole. But since the CS hole is already 300 millivolt away from that, so for convenience, we just pretending it doesn't exist. Since it's the population, the portion of population will be okay. And we also assume that the band structure is a simple parabolic. So we can write it down something like this. Then we want to calculate the number, so we just do it one term by one term. So first, let's see what the Gmax looks like. At HV is equal to H mu is 1.5. So the whole bunch of constants is 1.097 times 10e minus 15 divided by refractive index. Okay, so since here we already give you the N refractive index is 3.661. This is a number from the internet, so that's okay. We just need to put the number. It shouldn't be too far away. Second, since it is a bulk material, the transition matrix element divided by momentum matrix is 1/3. Since it doesn't have any preference in direction, it should be in all direction. So 1/3. And the momentum matrix element for gallium arsenide is 28.8 eV. Okay, so it's just numbers. So after putting into that, it doesn't look like so difficult now. So this is the 28.8 eV, and the H mu is 1.5 eV, the incoming light, and this is the CHH and the CLH transition matrix element divided by momentum matrix element. Now we only have only one thing left. Is reduce the density of state. That means how many pairs of the transition that will happen in such study. Okay, so this is the reduced density of state with a heavy hole. The bottom, if I write it down with the MH square, then it's the density of state of heavy hole. But since it is a transition between the conduction band and heavy hole, we need to replace that with the reduced density of state. And the reduced density of this state here is 0.057. Since and the MC is the effective mass in the conduction band 0.006. No, not so. 0.067. And for heavy hole, it is 0.4. If I I have a number here. For heavy hole, it is 0.38. Then after calculation, the effective density of state for the conduction band heavy hole transition it should be 0.057. We do the similar thing, the same thing, dipole. So the reduced density of state for such transition is 0.38. Alright. Then we just put all the numbers inside the equation. So this is MR powers 3/2, so 10, 1/2 pi. And since the MR star, this is the constant, you need to put the rest mass back in, or you will get a very unreasonable number. Okay, so this is the rest mass of electron. And this is the reduced Planck constant. Okay, the same. And the E is the photon you interested, 1.5 eV. And the EG is the band gap. No problem. Alright. Then since this is in electron volt, so since it's easier to do everything back in SI unit. That will make you make things safer, because you are trying to introduce other unit system. You might get some miscalculation at the beginning. So let's do everything with the SI unit first. So 1.5 y minus 1.424 eV to times the 1 electron volt, 1.602 times 10 e minus 19. Alright. So the whole number is a very large number, something like this. Since it is in SIU, you need to double check what the unit of every term. So it turns out to be joule per joule times millimeter inverse cubic. Then, since we are doing the first equation in the unit, in the first term in the okay, since we're doing this one in the terms of electron volt, right? Electron volt and the centimeter squared. Then we turn the value back to the corresponding unit. So it becomes what 1 joule is 1 electron volt is 1.6 times 1 e minus 16. Alright, so while you have joule minus 1, that means you put it in the inverse side, so it equal to 1.062 times. Okay, so then you can turn the joule minus 1 to eV minus 1. And the millimeter square turns into the centimeter inverse cubic. Okay, so it becomes a value like this. Then you can, this is the same procedure for the dipole transition. Okay, so what's the Gmax for the heavy load transition? It will be the first constant times 2.56 10e19. Then it is 4.92 times 10e3. So it is 4,920 cm minus 1. Yeah. Or yeah. Okay. So this is the maximum gain you can get for a conduction band and the heavy load transition. Similarly, we can do that with dipole. The maximum gain provided by the conduction band and the dipole transition is smaller. That's all because the action R is smaller. Because the dipole has a smaller density of state. Okay. effective the dipole have a smaller effective mass. A small effective mass give you a smaller density of state of a corresponding transition. Alright, so the total gap, you need to count both the transition between conduction band to heavy hole and the light hole simultaneously. So the maximum gap of a gallium arsenide complete and its maximum gain at 1.5 eV is around 7,600 per centimeter inverse. Okay. So this is the calculation we obtained. This is the figure, the plot from the textbook. So let's see what happens. So if it is 1.5 eV is around 830 nanometer, and that's what complete inversion, that means F2 is equal to 1 and 1 is equal to 0. Okay, it's around, slightly below 8,000. So our calculation is correct. Then now we have Gmax, but we haven't known what's the F2 and what's the F1. So we need to calculate the corresponding E2 and E1 first. Since we assume it's parabolic, the E2 minus EC at a higher level should be h bar squared k squared divided by 2me. Similarly, it's in inverse, so E2 minus EV minus E1 is h bar squared k squared divided by 2mh. Okay, so we know that since the transition is vertical, E2 minus EC times EV minus E1 should be at least the effective mass of hole divided by effective mass of electron. And 1.5 eV is 1.4 eV times a small energy difference at conduction band and the energy difference from valence band. So E2 minus EC is 1.5 minus 1.424. We need to subtract the backend first. Then do the partition according to the ratio of the effective mass. Since it is vertical, so the rest of them should have some part in the conduction band and some part in the valence band. And the partition need to follow this ratio of the effective mass. So it turns out for heavy hole, the E2 is 64.6 MeV above the band edge. But since we need to put a different edge here for the light hole, so for light hole, the E2 is the 43.6 MeV above EC. So it's also, although it's the same gap for the same wavelength, but it counts for the population of electron at a different energy level. Since the distance is fixed, 1.5 eV, but for light hole has a different curvature. So you cannot you have to calculate the probability of a different energy level here. Okay, so similarly, we can do that with the heavy hole and the light hole. So for the heavy hole, 1.5 eV give you the energy level 11.4 MeV below the valence band, or 32.4 MeV for the light hole band. Okay, so now you need to know what's the corresponding energy first. Okay, Then since we already tell you the injection carrier density to be 1e19, then we practice it in homework about where the Fermi level. And I'm not trying to repeat that here. Okay, so with 1e with the 1e19 carrier density, you can evaluate its position of Fermi level in the sense for each case. So for example, use the whole procedure is just the same. For the first one, we need to do the Bayes approximation and the dot K1 is 4.7. Then we know the position of the K of the EFC. Okay, let's take a closer look. For the heavy hole, the E2 is here, and its distance is 64.6 MeV. And give you a carrier density, you will get the BE is 9.65. So the 9.65 actually is already good enough because we already know what the position of EFC. So this is E2 and this is EFC. And this distance EFC divided by EC over KT is equal to 6.5. Okay. Right. This is done by the calculation with the given carrier density. This is done by the vertical transition. Since you need to do the vertical transition, you need to know what the actual position for the 1.5 eV for heavy hole. Okay. So the F2 is, this is the Fermi-Dirac distribution. Alright. So E2 minus EFC would be further decomposed into, so we simply will all use EC as the reference. So you will divide the EC then plus EC. So it becomes the lower part. So it's EC minus EFC over KT times E2 minus EC over KT. Okay. EC is 9.52 KT below that. So the first term is minus 9.65. And the second term it is 64.6 eV. And for 300K it is 25.8 MeV plus 1. Okay, so the answer is almost fully depleted. The carrier density is quite high. Similarly, for the light hole, because you really pump the FC at the too high level, the answer is still the same, pretty close to 1. The F2 is now almost fully occupied. Then similarly, you will do the same thing with the conduction band again. Then we find the heavy hole. So it's just the same procedure. I don't repeat that again. If we found that the probability of the CHH transition, the probability is 6.373. so not fully depleted yet, since the density of state is much higher at the valence band. So while the electron is almost fully occupied, but the valence band haven't fully depleted yet, since we have more higher density below. Alright. So for the heavy hole, the corresponding energy, the probability is 0.373. And for the light hole, it is 0.573. Because we already see that the valence band it is deeper for the light holes. Yeah. So since the corresponding energy is at the lower energy for the CLH transition, its population is F1 will definitely to be higher. Alright. So now we have all the number we need. Now we have the Gmax, F2, F1, F2 minus F1. So Gmax for the at 1.5 eV, the transition, the optical can is around 3000, and for the C to light hole band is about 1100. Still, the CHH hole dominates. That's because the density of state of heavy hole is much higher. So if you review that to see the numbers in detail, you will see the density of state and the effective mass is a very important number for the material optical properties. Alright. So for a 1.5 eV, the contribution from both transition need sum up since they have all contribution. So the total gain is the summation of these two values. It should be around 4000. Okay. So this is a schematic figure of the gain spec function slide. For light with a band gap smaller than Eg, there the density of state is 0 because there's no allowed state between that. So the positive gain is always 0. When it is excited, the energy between the EFC and the EFP again is also 0 here. This is the so-called transparent condition. The number between there will have a positive gain. So this point will shift to higher energy while you pumping the semiconductor harder. And the highest position will also shift it or be approaching to its Gmax curve. So if the pumping is weak, it should be the curve at the lower end. When it becomes stronger, you have a small region which might has a positive gain near the band edge, but it eventually merges to the minus Gmax. While you pumping harder and harder, there will be a segment with positive bandwidth between Eg, or in quantum world that will be the energy difference between the ground state. Because the lowest end is population inversion, the transparency condition, and the higher position. Unfortunately, you need to calculate point by point, but it's really hard work. We only practice it in class, so you unfortunately don't need to repeat the calculation for the bulk case. But the homework need you to do the case of the quantum wheels. So probably still a little bit some work to